Yeah, so this is Ulysse, guys. As you can see, he was my office mate at some point, and then he's been, yeah, it's very scary to be around him because he's like insanely productive. And for the, we talked about stuff that I think he's been thinking about for a while now. So looking forward to this.
Thanks a lot. Yeah, thanks so much for the invitation. I'm very happy to be able to talk about this work that I really like. There's a bit of a story behind this because this is a work that was prompted by a question that I'll talk about during the talk, during my PhD actually, with those two guys, Francesco Arzani and Robert Booth, and as well as a few other people at the time. So we started discussing on the topic of this talk. And there was something that was that was not right. I'll explain in a second. And we wanted to fix it. And we tried very hard. This was maybe 6-7 years ago, and we couldn't manage to fix it. And so, okay, our interest maybe died down for a bit, but we still had some of us like this question in the back of our minds. And so today I'm happy to say, okay, we've resolved that question. And this is, about that I'm going to talk right now. And in fact, the nice thing is that like while trying to answer that question, we stumble upon like many sort of interesting results. And overall, I think we can summarize what we're doing here by trying to address, in fact, a more general question, which is the title of this talk, which is, can effective descriptions of bosonic systems be considered complete? Okay, so let me explain what I mean by that. Before going there, a bit of context. What are bosonic systems? So I'm guessing most of you have computer science background. Maybe some of you actually already know what bosonic systems are. But anyway, I'll give a few examples. So bosonic systems, okay, they're ubiquitous in nature, and their statistics leads to remarkable physics. So this depiction here is the so-called Ongu-Mandel effect. And essentially, it's a fantastic physical phenomenon that says that if you send two photons, so two bosons that are indistinguishable, and they meet on a 50-50 beam splitter, so like a half reflecting, plate of glass, maybe, they will always bunch together. So they're never going to just cross and ignore themselves, if you wish. They will. This bunching effect is this so-called Ongu-Mandel effect, and it's actually at the basis of some of the quantum computational advantage experiments, because you might have heard of boson sampling. So boson sampling, you can think of it as kind of a large-scale generalization of this Ongu and Mandel effect back in 87. Okay, so it's like very fundamental physics, but of course, for the purpose of this talk and also my research in general, I'm really interested about what one can do using those bosonic systems. And two sort of main examples of architectures that now are used for quantum information processing using bosons are, let's say, quantum optics, quantum light in general. So here at the bottom left of the slide, you see this sort of artistic depiction of what the European quantum internet would look like. And there are many groups right now trying to make this vision a reality. So, okay, the idea here is that you have a bunch of quantum computers that are connected by photonic links, so connected through light, and processing quantum information in network settings. Okay, and on the other side of the spectrum of physical architectures, let's say, you have superconducting devices where you can use superconducting circuits to implement qubit quantum computations. But those devices, they also host what are known as bosonic modes that are represented here, and they have many, many different applications. So this is a nice picture that I stole from this paper that essentially explains, okay, how you can play with bosonic modes in the context of quantum metrology, quantum simulation, quantum communication, and quantum computation, which is the part that I'll focus on in the rest of the talk. So on the side of quantum computation, as I mentioned, photonics and bosonic systems, more in general, are at the basis of quantum computational advantage experiments. So this is a picture of the experiments performed by the USTC team in 2020, which sort of implemented a Gaussian boson sampling experiment. So really this sort of high-dimensional generalization of this Ongu-Mandel effect that I just showed before. And beyond just the quantum speed-up demonstration or this milestone of, like achieving one computational task that is hard for classical computers, you have many different actors, let's say, in the ecosystem that are trying to build universal quantum computers based on this. So I flashed out here a bunch of startups and big companies as well that are using either superconducting modes or photonics to try to build universal quantum computers. And on the right-hand side here, this is a picture from this paper down there, which showcased the first demonstration of quantum error correction in real time beyond the break-even point. So like when you manage to make your logical quantum information survive longer than the physical qubits that are underlying it. And this is done using a so-called GKP encoding, okay, that really relies on the bosonic degrees of freedom of a superconducting cavity. Okay, so all of this is to say that bosonic systems, they're extremely useful for quantum information processing, extremely promising at least. But from a theoretical standpoint, maybe what distinguishes those systems can be explained as follows. So typically, the way I tend to talk about this is like you have these two frameworks. One you can think of as discrete variable, and the other one continuous variable. And the main difference between these two frameworks is that the space in which you work, in which quantum states lie, is either finite dimensional, this is for the DV or discrete variable setting, or infinite dimensional, and this is for the continuous variable or CV setting. In those spaces, you have operators that act on the spaces. Those operators or observables, they allow you to represent like mathematically degrees of freedom that are bounded in the discrete variable setting. So you can think of this as like a qubit or the spin of an electron, the polarization of a photon, like two-level systems and so on. So finite degrees of freedom. And in the continuous variable framework, you can actually represent both bounded degrees of freedom and unbounded ones. And the two most famous, let's say, unbounded degrees of freedom are position and momentum. And the corresponding observables, they're typically denoted as Q and P. And they satisfy this commutation relation, which you might have seen before in a quantum mechanics class, that are called the canonical commutation relation for bosonic systems. Okay, now what's the difference when it comes to quantum computing with these systems? So with discrete variable quantum computers, like using qubits, so you have a bunch of gates that you can combine together to perform quantum computation. And there's a notion of universality, like when is a quantum computer universal? And the answer is, by definition, this is when you can combine your set of gates to approximate any unitary evolution to any desired precision. Whereas in the continuous variable setting, the definition is somehow a bit more restricted, a bit more physically motivated, let's say. And the original definition that was introduced in 1999 by Lloyd and Bronstein is that, well, a universal continuous variable quantum computation is going to be a sequence of gates that can approximate any unitary evolution that is generated by polynomial Hamiltonians. And so by polynomial Hamiltonians, we mean Hermitian observables that you can write as polynomial of Q and P operators here. So polynomials of position and momentum operators. So this is somehow, okay, some restricted class of Hamiltonians that still appears a lot in bosonic systems. And so they decided back in 1999 to base the definition of continuous variable quantum computations on that class of Hamiltonians. And this is still the definition that is used in today's literature. To give you a bit more concrete examples, so these are examples of universal gate sets according to those definitions. So the Hadamard, CNOT, and T gates in the case of qubit quantum computers. And here, okay, you have a bunch of gates. This is, let's say, the Fourier gate, the CZ gate. Here you have a cubic gate. Here you have a displacement gate. But essentially, the only thing that you need to care about here is that those are unitary gates that are generated by Hamiltonians that you see are either here quadratic in the Q and P operators, or cubic here, and this one is linear. So they're all polynomial Hamiltonians. Okay, and as a result, I mean, there has been much more work on the discrete variable setting. So this is sort of historically because, well, of the way we do classical computing, but also because of the availability of qubit platforms. It's much easier to control a two-level system than let's say an infinite dimensional system that you get in a bosonic mode. And as a result, like one of the landmark result that exists in the discrete variable framework, but not in the continuous variable framework, is the so-called Solovay-Kitaev theorem. And so what this theorem says is that when you have a gate set that is universal, that you can build sequences of to approximate any unitary evolution, the Solovay-Kitaev theorem actually ensures that this can be done very quickly, like the size of the sequence, the length of the sequence of gates that you need to combine given a target unitary evolution is very short. And so in the continuous variable setting, this is a very hard question because you're dealing with infinite dimensional spaces and bounded operators, and it's sort of not so clear how to combine these operators together to approximate unitary evolutions. So far, result like Solovay-Kitaev theorem is missing. Okay, one thing that I want to emphasize here on that slide is what we typically refer to as the continuous variable universality problem, which is the problem that is this definition of universality in the continuous variable regime actually sound? Is it a good definition? In the sense that it seems that it's kind of a bit restrictive, like we have taken this specific family of Hamiltonians and we call evolution generated by such Hamiltonians universal. But it could totally be, as far as we know, that actually these are not universal in sort of the natural sense of can I go anywhere, from one point of the Hilbert space to another point of the Hilbert space. As far as we know, maybe polynomial Hamiltonians, they only allow us to explore a strict subset of the Hilbert space. And more generally, when we're looking at polynomial Hamiltonians and the quantum computations that we can do based on those Hamiltonians, one could argue that we're actually looking at a restricted model of quantum computations. This is a bit as if in the discrete variable case, I was telling you, oh, universality is going to be everything that you can do using unitary evolutions that are generated by Clifford Hamiltonian. And so if you were doing this, you would, end up with a model that is called Clifford quantum computing, which we know by the Goddess-Mandel theorem that you can simulate efficiently. So, this is, of course, a kind of a made-up example, but this is just to say this at least deserves some investigation. Like, is this a good definition of universality? Okay, and so on this slide, you see that sort of everything is green and nice on the discrete variable quantum computing framework, and everything is red and complicated in the continuous variable regime. So of course, this is an artifact of the way I built the slide, but it has some counterpart in the reality in the sense that when physicists and computer scientists care about continuous variable systems and bosonic systems, they have to rely on effective descriptions of bosonic systems. Okay, so this just means, we have this kind of complicated mathematical framework. Let's just simplify it, get some effective description, and we'll use that to describe our bosonic systems. And this typically comes in two flavors. So one is simplifying the state space. So instead of working with this infinite dimensional Hilbert space, we want to simplify this. And the other is to look at effective dynamics. So maybe the dynamics could be, any sort of weird Hamiltonians with unbounded operators, and maybe we'll restrict this to specific families. So in practice, this looks like this. You have the, let's say, true Hilbert space that is infinite dimensional, but you're going to truncate that infinite dimensional Hilbert space to a finite dimensional one based on some effective dimension, some truncation level. And the way you do this physically is based, for instance, on energy bounds. So you have some Hamiltonian that measures the energy that has some unbounded spectrum. But in the real life, energy is bounded. You measure the energy, you get some finite value. That's sort of a finite total energy of the universe. So in principle, you could cut off that spectrum and restrict to some subspace that is finite dimensional. And in fact, this is something that is actually necessary. Like if I want to simulate a bosonic system on either a classical computer or a quantum computer with finite degrees of freedom, I need to do a cutoff. I cannot just track infinitely many coefficients in the Hilbert space. So this is something that you have to do if you want to understand the physics of bosonic systems. And with regards to dynamics, so you can restrict to specific families of effective Hamiltonians that maybe are easier to deal with. And so one common choice is to work with those polynomial Hamiltonians because they're sort of very natural, effective Hamiltonians for a bunch of physical platforms. And in particular, this has led Lloyd and Bronstein in 1999 to define continuous variable universality based on those Hamiltonians. Okay, and the question that we ask is what can go wrong? So, okay, we can use those effective descriptions to simplify a bit the setting, but what could go wrong with these type of effective descriptions? So the first remark that I want to make for like truncating the state space is that the sort of basic mathematics structure that there is about bosons, these canonical commutation relations, it turns out that they're impossible to satisfy in any finite dimension. And so this, you can convince yourself pretty easily, like if you look at this relation here. So Q and P are the position and momentum operator, and I here is the identity operator. And if you assume for a second that this could be achieved on a finite dimensional Hilbert space, and then you take the trace of this expression, on this side, you'll get a trace of a commutator that will give you 0. But on that side, you'll get I times the dimension. So not only it's just not possible to exactly have this equality, but the higher the dimension, the more you're going to see a discrepancy between those two parts. So this is kind of just a mathematical sort of intuition of, okay, we need at least infinite dimensional Hilbert spaces to write down such an equation. Okay, and you have other sort of signatures of infinity, which is, for instance, this result that the set of quantum correlations differ in the finite and infinite dimensional cases. So they are quantum correlations that you can produce by measuring quantum systems that you can only produce if you're working with an infinite dimensional system. So these are two things that, go for it. Yeah.
I have a question. So when you say set of quantum correlation differ, you mean the set means those by the what set is coming? It's the state of states what you are referring to, or what exactly you are referring to as set here?
Say that again. Sorry.
So I am saying what exactly you are referring to as a set in the context of quantum correlation.
Yeah, so this is a set of all the probability distributions that you can produce by measuring some P of EM on some quantum state.
Okay. I want to have a very dumb question, Ulysse. So how do you square the fact that the traces are different on the left and right hand side in infinite dimensions? What goes wrong in the argument?
Absolutely. Great question. So what goes wrong is that those operators on both sides actually are not trace class, meaning that their trace is not even defined because it would be some sort of infinite series that diverges. So you just cannot take the trace in infinite dimension. And it turns out the way you can interpret this relation is to say on each state, if I act with the thing on the left-hand side, I will get the same thing that if I acted on the right-hand side. Okay, so there's a domain essentially problem if you try to take the trace. Okay, so this is what could go wrong with effective state space. Just two examples. And with effective dynamics, well, here the objection is maybe a bit more natural. It's just to say, well, sure, you have many bosonic systems that have native polynomial Hamiltonians, but you also have many bosonic systems where this is not the case. Just think hydrogen atom, or here I gave you the example of like Josephson junction, where you get Hamiltonians that look like this. They're sort of cosine of some unbounded operator. And here you could come and say, oh, maybe I can, expand this cosine as a Taylor series, truncate, and approximately this is going to give me a polynomial. But you can in fact show that there are many cases where this is just not, those two operators are just not equal. You cannot just replace some analytic function by its Taylor series because it takes as an argument an unbounded operator. So here the situation is kind of subtle. And then there is the CV universality problem that I talked about earlier on, which is that, okay, as far as we know, polynomial Hamiltonians, they could generate only a restricted set of unitary evolution. So we might want to revisit the CV universality question. Okay, and so this motivates this general question that is at the basis of our work, which is, can we trust these effective descriptions to capture real effects?
And one small question.
Of course, yeah.
Okay, so sorry, there was some. Okay. So the question was, when you write these polynomial Hamiltonians, are they all necessarily physical in the sense that I suppose at the lab until quadratic it sort of makes sense, but beyond that it starts getting more difficult. Is there like, so the question is it physically easy to implement all of them? All
no,
polynomials?
No. So the answer is like it depends on the platform. For instance, like this guy here, cos q. if you're looking at a superconducting cavity, this is in some sense, for a theoretician, this is easy to implement. If you're trying to do this in a quantum optics, like usual tabletop optics setting, it's essentially impossible. So it depends on the platform, what you would call physical and unphysical. But generally, the intuition that you just gave, I think is quite right. That the higher, the non-linearity you want to go in terms of like the higher the degree of the polynomial, the harder it's going to be to control. Yes. So ideally, you would want to only work with polynomial Hamiltonians that are low degree, and then combine them by sequences of gates to reach higher degree. And this was the original proposal by Lloyd and Bronstein. So in this gate set, maybe I can quickly show you this. In this gate set that I showed, this is, let's say, their universal gate set for their definition. And you only go up to degree 3. And if you want to access higher degree, you sort of braid those gates together to like generate higher degree through commutators. That would be the idea.
So is it clear that there should be like a universal effective description? It looks like from what you're describing, the effective description would depend on the platform. Is it something to worry about, or?
It is something to worry about as well. Yeah. No, there are other things indeed that. So here I'm just sort of giving a bunch of arguments to motivate the question, but I agree. There are other points where you could say, well, is it even just a reasonable gate set to start with? Like maybe it just does not apply to the platform that you're looking at, and you should just ditch it altogether. Yeah, I think that's a good comment. Okay, and so our results on that like, can we trust effective descriptions of bosonic systems? Is yes, we can. And if you're talking to physicists, like typically they would say, sort of, I knew it all along, like somehow, yeah, of course you can truncate the Hilbert space. Of course you can work with polynomial Hamiltonians and it's going to work fine. But there are like two aspects that are important, I think, to this work, which is, so first, it's actually not so trivial to prove. And the other thing is you learn actually many things by trying to answer this question. And so this is what the rest of the talk is going to be about. So our answer to this question relies on two technical results. So one is about effective state space. The other one is about effective dynamics. And the one about effective state space, in essence, says, yes, if you have some unitary dynamics, you can truncate it. And more precisely, what it says is that if you start with some target physical unitary evolution on some infinite dimensional space, and I'll explain a bit more in detail what I mean by physical in a second. So if you start with this target infinite dimensional evolution, you can rigorously approximate it to arbitrary precision by a sequence of finite dimensional unitary evolution. So this really says, from a rigorous mathematical standpoint, yes, you can truncate unitary evolution, and their truncation can also be taken as a sequence of unitary evolutions that are finite dimensional. And on the side of effective dynamics, the second result says that polynomial Hamiltonians are actually DV universal in the sense that now take any finite dimensional unitary evolution. So this could be, let's say, the unitary evolution generated by a qubit circuit over n qubits. It turns out that for any finite dimensional unitary evolution, you can exhibit a polynomial Hamiltonian that will generate exactly this finite dimensional evolution. So somehow the polynomial Hamiltonians, they're super expressive. They really allow you to exactly represent any finite dimensional unitary evolution. Okay, so I'm gonna.
So before we go on, I just wanted to quickly check: is there a notion of efficiency here that one thinks about, or?
Yes, it's going to show up, and so I think that this would be the next question. Like you would want sort of a Kitaev essentially for sequences of evolution, and I'll touch upon this towards the end of the talk.
So at the moment, it just says that it can be done, but it doesn't say anything
exactly.
About how many gates.
Yeah. Exactly. So, but so all those, as you'll see in a second, you'll see that all those results, they're actually highly constructive. So you will get a bound that maybe is not like so tight, but it will tell you, oh, this is how high you should cut off. And here it will give you an exact construction of, yeah, this is the polynomial Hamiltonian that you should pick. But okay, let's get there.
But then how
So-
does it square the cosine example you gave earlier? That you said right, that the cosine can never be approximated. So you're
Yes,
saying it can be
exactly.
approximate?
It can be exactly. No, that's a great point. So the cosine is my Hamiltonian. Okay, if I have a system where it's the true Hamiltonian, let's say, that system is going to undergo, like, let's forget about losses and everything. Let's say everything is unitary. So it's going to undergo a unitary evolution that is just the solution of Schrodinger's equation for the Hamiltonian, that is this cosine thing. And what we're showing is that this unitary evolution you can cut off. So you cannot really cut off the cosine object, but you can cut off the unitary dynamics. And okay, the mathematical sort of reasoning behind this is that while the Hamiltonian is unbounded as an operator, the unitary operator that it generates by exponential is a bounded operator. And so this is what we can leverage to perform the truncation. And here the situation is going to be a bit more subtle, but you'll see in a second. Okay, so unitary truncation. So let me maybe explain a bit what I mean by physical unitary evolution, like what are those unitary evolutions. So a bit of notation to do this. We are in the continuous variable setting, so we're working with this infinite dimensional Hilbert space, and it has a countable basis, so it's this represented by those integers n. This is typically referred to as the photon number basis in optics, for instance, or the particle number basis. And it comes with a number operator, which is just diagonal in this basis, and it measures the number of particles there is in a given mode. And so in the rest of this talk, when I mention the energy, what I will mean by this is the average particle number. So typically when you measure energy with respect to some Hamiltonian. And so this is the Hamiltonian that we use to measure energy. Is sort of the standard way of measuring energy in bosonic systems. And the goal essentially everywhere is going to be to replace this infinite dimensional Hilbert space by a truncated version, okay? Where now you see that I'm sort of truncating like strongly. I'm cutting off the Hilbert space to get something that is now finite dimensional. And this n now would represent the maximal number of particles, okay? Okay, so with this, what are physical unitary operators? So physical unitary operators, they're defined loosely speaking, let's say, by the unitary evolutions that map states of finite energy to other states of finite energy. Okay, and so we're just putting some bound like this. So this is saying, this mathematical equation is saying, if you start from a state that has at most big N particles, and you evolve it under some unitary, then the average particle number after the evolution cannot be infinite. Okay, and so this is when a unitary operator satisfies this condition, we say it's a physical unitary operator. And again, this is sort of a restriction that makes sense in the sense we don't expect anything in nature to produce something of infinite energy. And I emphasize that it does not matter like how high this quantity is, right? Like this EU of n, you can think of it as like, oh, this is the maximal energy that I can get to using my unitary evolution if I start from a state that has particle number n, and I just want this thing to be finite, but that's all. And finally, this is a bit more technical, but we are trying to approximate operators. So when we're doing this truncation, we're looking at an infinite dimensional object, a unitary operator, and trying to replace it by a finite dimensional one. And so for this, we need a notion of approximation. And we need a notion of topology. And so the right topology to choose in infinite dimensions is the one induced by the so-called energy constrained diamond norms. So the definition is this. So if you know what the diamond norm is essentially the same as a diamond norm, but you just add the fact that you're looking at like states that have a bounded average energy. And intuitively, you can think of this as I want to compare two quantum channels, and this norm will induce a distance that is a measure of distinguishability, and it's how well I can distinguish two channels, like using states that have a bounded energy. Okay, so with all these preliminary material in place, let me give a slightly more formal version of the unitary truncation theorem. So again, we start with this infinite dimensional physical unitary evolution, and we're trying to approximate it to arbitrary precision by a sequence of finite dimensional ones. And so what this theorem says in equation is that if you pick an effective dimension that is high enough, so it's this quantity here, d is going to be my effective dimension, how high I am truncating, then you are sure that you can replace your target unitary operator u by some finite dimensional object vd. Okay, and here in the equation, there's a bunch of other things that I'm going to explain. So what we're trying to do right now is take this infinite dimensional object, replace it by a finite dimensional one. But of course, to compare the two objects in a meaningful way, we need to compare two infinite dimensional objects, which is why this finite dimensional unitary here is in direct sum with some other unitary operator v on the rest of the space. And what this equation says is that there is a truncation parameter d such that you can pick this finite dimensional unitary evolution in such a way that no matter what you put on the rest of the space, the distance between these two objects will be small. Okay. And so if sort of maybe to fix ideas, you can think of your infinite dimensional Hilbert space as having this infinite countable basis. And this is what this VD plus V would look like. So on some finite dimensional subspace, you would have the action of VD. And then on the rest of the space, V acts. But of course, if you start in this finite dimensional subspace, you stay in the finite dimensional subspace. You have this direct sum approximation. Okay, and so this answers, like, let's say, part of Atul's question about efficiency. So this is telling you how high you need to cut off directly depends on a bunch of parameters. So there's 3 parameters here. You have E here, which is some sort of free parameter that is parameterizing the topology that you're playing with. And you can show that these convergence statements, they're independent of the choice of E. Okay, so the choice of E here is just going to affect the speed of convergence, but the statement will remain true, okay, no matter the E. Epsilon here is just how good is your approximation, so your approximation parameter. And then there's this EU of that effective dimension here. And this is sort of saying, if you have a unitary that generates a lot of energy, then of course you need to cut off a bit higher. Okay, and that's all in all, this is very intuitive, but really not so straightforward to prove. But it's materializing this intuition of like, the more energy is involved in the evolution, the highest I will have to go to cut off. And in some sense, this is sort of tight. So this is not something that we've thoroughly sort of explored, but we have ideas of examples where it feels that you cannot do much better than this in the parameters. But this is not something that is proven so far, but we have good reasons to believe that you have to pay this price in general. Okay, and the cool thing about this result is that the proof is constructive. So the way it works is kind of intuitive. This is, you just start from your infinite dimensional unitary. Then you truncate, so you take the upper left block, but now you're looking at let's say a finite dimensional submatrix of some infinite dimensional unitary operator, and so because you just took this block, it's maybe no longer a unitary, and so there's a second step that rounds it to the nearest unitary in some sense, which is this VD at the end. Okay, so this is about the technique. But what we care about here is that this result, so not only it's sort of say, oh, our intuition that we can cut off is fine, but it's also giving you a rigorous upper bound on the dimension that you need to simulate bosonic dynamics up to a required accuracy. So you get this provably sort of precise truncation argument. Okay, any questions at this point? Okay, so if not, I can dive into the second result.
Please, yeah, sorry, I wanted to ask something quickly.
Of course.
So,
yeah.
So yeah, just to make sure that I'm following. So V hat is a polynomial of Q hat and P hat.
Oh, no. So this, sorry, yeah, maybe I should have said this earlier. So there's no polynomial here. I'm just giving you sort of, you have a target operator, which is some infinite dimensional unitary evolution. And I'm telling you how to truncate, but there's no polynomial involved at any point.
I see.
So this is fully general. How to truncate an infinite dimensional unitary operator.
Right. So okay. So sorry, this is going to be a little bit dumb because I'm slow. So we had D is the truncation, right?
Yes.
And how do you compute the truncation? Is it just that you remove the terms with higher than the number of particles?
Yeah. So
is that what by truncation?
No, so it's this two-step process. So you start, U is your target. You start by really truncating. So you just take the top left submatrix like this. And but now the problem is this object is no longer unitary. So you do this kind of essentially like Gram-Schmidt orthonormalization technique, and you extract a unitary operator out of this. And there's a bunch of other sort of subtleties, but the high level idea is this. Yeah. So truncate and then round it to a unitary.
Let's see. And so then the size of BD would scale with like there's no notion of number of qubits now, right? Because it's in bosons, so it's slightly different.
Yeah, it's the same. Like there's this, you could introduce like a scaling parameter, which is the number of, it's called modes, but it's really the same. Here I'm just showing you the single mode thing because the notations are easier. But the true statement would also scale. Yeah, if you can do this multimode, and essentially the idea is that these energy parameters, it's going to be the total energy. You can probably think of it as like you add a number of modes whenever there's an E. Right, because like the energy maybe would be some constant amount per mode, okay, and so you'd expect a scaling that that scales like this. Any particular when you
sorry, go on.
No, I was just about to say, like, if you have a highly multi-mode system, it would be hard to compute this truncation. So it would scale. It could scale terribly. So it could. No, so it's not necessarily easy, but somehow it's something. It's an existent thing. It should be expected because in some sense we're trying to replace a Q mode by a qubit. But if now I have n Q modes, I can replace this. I can replace this by n qubits maybe. But this n qubit is still like some unitary matrix of the size d to the n. It's very big, so it's not going to be efficient.
Thank you for the clarification.
No, sure.
Sorry, I had a quick question as well.
Yeah.
So, this theorem is about the existence of a VD hat, right? It doesn't say anything about the algorithm to like come up with VD hat.
It doesn't say anything about what? Sorry.
The algorithm to find VD hat, right?
Oh no, it gives you the algorithm. Yeah. The theorem doesn't say it, but it's here. There's a constructive proof, and it gives you the algorithm to find VD. And this algorithm is take the top left submatrix of U of size d+1 by d+1, and then do a bunch of manipulation to extract out of that a unitary matrix, which you can think of as taking again a submatrix of this thing and doing a Gram-Schmidt orthonormalization, and extracting the change of basis matrix out of this.
So the algorithm is efficient as well, like, but how? Like, what does efficiency mean?
So here, So here, if you have a single system, a single mode, the algorithm is efficient in the sense that it's going to be polynomial in all the parameters that are written down here. But if you have multiple modes, so multiple subsystems, just like multiple qubits, then it's going to be efficient in the dimension of the resulting Hilbert space. So it will still be polynomial in this D, but now this D will be the effective dimension of like n qubits, let's say. So something that scales exponentially with n. So it's not going to be efficient. But there's no way you can there's no way you can avoid that. Like somehow, if you sort of just truncate a unitary, it will leave on some exponentially big space. And so just to list the coefficients, you would need some additional assumption. Maybe you have a sparsity assumption on the unitary matrix, and then you can make it work. But otherwise, I don't think there's a way to avoid that.
Thank you.
So if the Hamiltonian is like a polynomial of these Q hats and so on, then do we expect the VD hat to be efficiently computable in the number of modes? Or you think that's reasonable
So
loss
no,
that is to be for? No, okay.
no. So what you would do, you're going to see in a bit, but what you're going to do is you're going to go mode per mode. And because typically, okay, here we're really thinking like unitary dynamics. So we don't have any structure in mind. But if you think quantum computing, then you have gates, right? So those objects, they would only ever be unitary gates acting on maybe two modes at the same time, or k modes at the same time, where k is some constant.
Right.
Now, those you can truncate efficiently. And then,
Right.
okay, you have to work a bit to show that the combination of all those truncation is kind of a valid approximation of the whole circuit. But that would be the idea. Yeah. There would be ideas like this towards the end of the talk. Yeah.
I see. So then what prevents the Solovay-Kitaev statement from arising? Is there like an obvious block? Well, I'll ask later actually. Sorry. Yeah, go on.
Yeah. You'll see. Essentially, the answer is nothing, and this will be one of the results of the work. Yeah. Okay. So let me just touch upon this second result, the second technical result, and this one. It goes now a bit in the other direction. So before we had this infinite dimensional object and trying to truncate it to some finite dimensional unitary operator. And now we're sort of reversing the statement. I'm saying start from any finite dimensional unitary evolution. So now just your usual unitary operator on the finite dimensional Hilbert space. And I'm telling you that I can generate this thing exactly using a polynomial Hamiltonian. Okay, so recall that this polynomial Hamiltonian, so it's polynomial in these Q and P operators. It acts on an infinite dimensional Hilbert space. Okay. So how does that look in practice? Well, so here's the setting. You take some linear operator A. Let's say it's Hermitian in this context. So I have some Hermitian operator on some finite dimensional Hilbert space. So here it's HD. And this theorem tells you, given the description of A, I can find a polynomial P of A and some some additional operator A prime such that P of A takes the following form. So it's exactly A on the subspace HD. And then it's in direct sum with some other operator A prime. Okay, so again, this is the representation that you should have in mind. So this first block here, it's the HD part, like the finite dimensional subspace of the infinite dimensional space. And then there's some leftover operator. And this is sort of necessary because we are trying to compare something finite dimensional with something infinite dimensional. And so this is what we mean when we say PA here generates exactly the evolution A. It does so on the subspace, and it's in direct sum with something else that we don't really care about. Because again, if you start in this subspace because of this block diagonal structure, you stay in the subspace. Okay, and as a result, you can exponentiate the statement. It's not so trivial, like because again, these are unbounded operators, so they are domain subtleties that you need to take care of. But you can show that the unitary evolution now generated by this P of A is actually the same as the unitary evolution generated by your original Hermitian operator, your original Hamiltonian on the subspace. Okay, so here there's no notion of approximation. Everything is exact. In fact, I stated it here for Hermitian operators, but it works for any linear operator. You can always build a corresponding polynomial, which will exactly reproduce the operator that you care about. Okay, and so the way we do this is also constructive. The high-level intuition of the proof is that you're going to decompose your Hermitian operator in a certain basis of the finite dimensional space, and coefficient by coefficient, you're going to run some interpolation polynomial arguments to build up coefficient by coefficient the polynomial, the final polynomial, and you just sum all the different polynomials. And in the end, you'll manage to construct the corresponding polynomial that acts exactly as A on the subspace. And okay, two consequences of this result. So the first is that typically we think of, this is a bit what I was presenting before, we think of using classical computers or quantum computers, let's say qubit based, to simulate bosonic dynamics. But actually now we're starting to have those physical platforms that are like controlling bosonic degrees of freedom with very high precision. And so this type of result, it opens the door to actually reversing the situation. You could say, oh, I have these bosonic platforms that I control super well, and maybe I can tune my interaction Hamiltonian, my polynomial Hamiltonian. And now this tells me that, oh, I get this sort of universal simulator in the sense, if I have now some finite dimensional physics that I want to simulate, I can just reproduce, I can program my simulator to reproduce the polynomial Hamiltonian that corresponds exactly to this finite dimensional physics, and study it on my Bosonic simulator. So, okay, this is kind of a bit preliminary idea, because of course you would need to be able to implement this thing, but this is actually an idea that some of so without this kind of universality proof, but some people that have these kind of Bosonic simulators started looking at, so trying to reproduce quantum Hall effects using photons and these kind of things. So this sort of opens the door to pushing this to essentially kind of a universal setting.
And is the scaling thing still the same in the sense that, like, say my discrete variable system is coming from, say, I don't know, n qubits? Does the approximation go okay with n?
Yeah. So here, what would happen is, again, it would scale badly. So if I have
it goes with the dimension, is it?
It goes with the dimension. So you'd get exactly this kind of 3D. So it would be 3D times 3D times 3D for each D. Yeah.
Right.
Exactly.
Yes. And do you expect it to be efficient? Like if you additionally had the structure that it's coming from n qubits, the discrete variable system, you think there's a chance that this could be efficient? Assuming that the unitary is efficient somehow to begin with?
Yeah, not so clear. I think this is sort of open, and I'll discuss a bit in what comes next. Yeah.
Also, maybe one thing I would mention before you move on is that we don't see a pointer. So for some reason, so you have to.
Oh.
Yeah. I don't know why that is, but just so you know when you're presenting. Oh, I think you do see it very small. No. I think you see it. Sorry, it's my bad. Sorry. Okay.
No. But now you don't see it, right?
No, I don't. Now I don't see it.
Okay. Yeah. No. So you were not seeing it. It's just I changed it from now you see it. Okay.
Oh, it's on a different screen. Okay.
Yeah. So you'll see me maybe. Oops. Oh, I broke everything.
Oh, no.
All good?
We don't see a screen share yet.
Okay.
I think maybe the display cable got disconnected.
Yes. Okay. Hopefully.
Okay.
Just give me a second.
Question.
Okay. It crashed. So let me just actually share my own screen, and I'll do it this way. That's okay. So you should see my screen now.
Yes.
Okay. Yes.
Yeah,
okay. Now you'll see. No worries. It's good that you tell me. Yes. So maybe one point that I wanted to emphasize as well is, like, already this result tells you that those polynomial Hamiltonians are in some sense universal, in the sense you can go anywhere in the Hilbert space. Okay, what is that? Why is that? This is because if, let's say I start from some reference state 0, whatever that is, and I want to reach some state psi. So what I can do is I can truncate this psi. So psi, I can expand it in this infinite basis. It will be some normalized state. So there is sort of a level that I can truncate in such a way that I'm very close to psi, but now I'm looking at a state that lives on a finite dimensional space. And now if I do the same for this state, I'm looking at two states that live in some finite dimensional space. Okay, so I can build a finite dimensional unitary that connects those two objects. Okay, that sends the first one to the second one. I can essentially diagonalize this unitary. I can deduce the Hamiltonian that generates that unitary. I can use the theorem here to implement that Hamiltonian with a polynomial Hamiltonian. Finally, I can exponentiate that polynomial Hamiltonian. And all in all, what this will have achieved is that I will get a polynomial which generates a unitary evolution that takes me arbitrarily close from the starting state to the target state. So this is really saying, like, as a consequence, as a direct consequence of this theorem, This is saying that you can do universal state engineering, to put it in words, with polynomial Hamiltonians, or said differently, I can go anywhere in the Hilbert space using polynomial Hamiltonians. So this is already good news for the universality definition. It's not the full universality, because when you're caring about quantum computations and universal quantum computations, you want to approximate unitary gates, not just their action on a specific state. But already this is something that was open for quite a while, that you can, like, these give you a universal controllability in the Hilbert space. Okay, but I think that the most interesting part comes when you actually combine those two things. So unitary truncation here tells you start from the infinite dimensional setting, approximated by a finite dimensional unitary. And the second theorem tells you if now you have a finite dimensional unitary, you can generate it exactly by a polynomial Hamiltonian. So of course, if I combine the two, what do I get? I get that any infinite dimensional physical unitary can be approximated by unitary gates that are generated by polynomial Hamiltonians. Okay, and this is this really two-step process. I truncate, I round it to a unitary, and then I take this finite dimensional unitary and I replace it by a polynomial Hamiltonian. Okay, and this is really the continuous variable universality of polynomial Hamiltonians, because now we have shown at the operator level that you can rigorously approximate unitary evolutions in the infinite dimensional space by sequences of unitary gates that are generated by polynomial Hamiltonians. Okay, and the natural question, which was raised earlier on by Atul, is that, okay, but is any of this efficient? And in particular, can we hope to get something that looks like a Solovay Kitaev? And as Atul anticipated, actually, there's no real obstruction. So you could say, I start from the DV Solovay Kitaev, which says any finite dimensional unitary can be approximated by a short sequence of unitary gates from any universal gate set. And you can use that as a subroutine to actually get this continuous variable version of a Solovay Kitaev. So it's a weaker version of the theorem. I'll explain why. But it states the following, that any infinite dimensional physical unitary evolution, you can approximate it rigorously to arbitrary precision by a sequence that is short of unitary gates that are themselves generated by polynomial Hamiltonians. So it tells you, okay, for some universal gate sets that are based on polynomial Hamiltonians, yes, you will be able to approximate any unitary using short sequences. Okay, so how does that work? So as I said, it uses the discrete variable Solovay Kitaev as a subroutine. And it's quite intuitive. So it says you start from your target unitary evolution, infinite dimensional. You truncate it to get some finite dimensional unitary evolution that approximates it to a good precision. Now this is finite dimensional. So I can pick my favorite discrete variable gate set and apply the discrete variable Solovay Kitaev theorem. And what I will get is a short sequence of finite dimensional unitary gate from any universal gate set, discrete variable universal gate set that I want. Now I can use the universality, the exact universality of polynomial Hamiltonians on that finite dimensional subspace. So each of those gates in the short sequence, I can realize by polynomial Hamiltonians individually. And the result is this short sequence of unitary gates that are generated by polynomial Hamiltonians. But now I can consider them back as being infinite dimensional unitary operators. And then, okay, most of the proof now comes into making sure that all of this is sound, that not at the level just of finite dimensional unitary gates, but at the level of infinite dimensional operators, the original target unitary and the final short sequence of infinite dimensional unitary gates generated by polynomial Hamiltonians are actually close. Okay, and so let me try to summarize what exactly these theorems prove, because it's not like an all-powerful Solovay Kitaev theorem. In particular, there's going to be efficiency problems that come in, and that are sort of expected. But okay, this is what the theorem essentially says. It says that if you pick some universal gate set for qubits, so over some finite dimensional space of dimension, let's say d+1, and then you do that for all d, so you could pick, let's say, a family for all d of finite dimensional gate set. These universal gate sets in the finite dimensional setting, you can realize them using continuous variable gates generated by polynomial Hamiltonians, and those will satisfy this Solovay Kitaev theorem. Yeah, there was a question.
Yeah, sorry, that may just be me hitting the table with my
Okay.
bar.
No worries. Okay, so the point here is that I mean the catch or somehow the way those universal gate sets of polynomial Hamiltonians are being constructed is that you need sort of like one gate set for each effective dimension, and then it's just combining all of them together that you get this universal gate set that satisfies Solovay Kitaev. And if you remember this construction of dv universality of polynomial Hamiltonians, the degree of the Hamiltonians, they scale with the dimension. Okay, so all in all, this is a nice result, I think. Like we get a Solovay Kitaev theorem that works for universal gate sets generated by polynomial Hamiltonians. But those polynomial Hamiltonians, they have like sequences of degrees that can go very high. Okay, just wanted to emphasize this. Okay, and I'm going to conclude here. This is the last slide. So we looked at this, let's say, systems of bosons, and the first result that we showed was this unitary truncation to an effective dimension. And okay, to me, the main application of this this result is to have this guarantee on the accuracy of the simulation of bosonic systems when you're looking at unitary dynamics. And this allows you to effectively represent. So here you can use this result like both for classical simulation, but also for quantum simulation, because the truncation is really unitary. You get an operator that, well, okay, is unitary on a finite dimensional space. So you can realize it with a qubit system. And then if you go the other direction, if I start from something finite dimensional, what we showed is you can you have universality of effective polynomial Hamiltonian, so you can realize it like any finite dimensional evolution using those polynomial Hamiltonians. And the two main applications here is like, oh, maybe I can use Bosonic simulator to simulate finite dimensional systems. And also this resolves this quantum control question of like, can I go anywhere in the Hilbert space using polynomial Hamiltonians? And finally, when you combine those two results, well, you get universal gate sets that are based on polynomial Hamiltonians, which satisfy this Solovay Kitaev theorem. Okay, so I'll just flash out a bunch of open questions, and if you have more, I'll be happy to answer them. Thank you.
Let's maybe time up the. Does anyone have any questions?
I had one question.
Yeah.
So, can you go to the last slide?
This one.
Yeah, right. So the last equality, so it's a short sequence of finite dimensional unitary gates, right?
Yeah.
Okay, so it isn't infinite dimensional unitary gates.
No.
Okay. And why do we know that like infinite dimensional unitary gates can be like generated by a short sequence of polynomial Hamiltonians?
So yeah, this equality here is a tiny bit misleading. This equality is like for each gate in the sequence here, you can append some random operator on the rest of the space. So you have the unitary gates on your finite dimensional space, and you can append in a direct sum structure some random operator in such a way that this thing now is a polynomial Hamiltonian. Maybe it's a bit clear if I show, yeah. So this would be the statement. Now, this is your unitary operator, if you wish. You build a polynomial Hamiltonian such that you realize exactly this equality on the finite dimensional subspace. And then on the rest of the space, there's something that you don't really care so much about, right? On the rest of the space. And the reason why you don't care about it is because in the unitary truncation theorem, the quality of the approximation between the unitary gate and the truncated version does not depend on what you append to the truncation. So it's like you get the truncation for anything that I append, it will be still valid. And so this is how you sort of resolve this. I agree there's kind of an ambiguity in the slide here, but this thing is equal in the sense, yeah, I can append anything like, okay, I can append the right thing here, which does not affect this previous argument at this step or that step, and such that this equality is true.
Yeah, right. Thank you.
Sure.
Hello.
Hello.
So I had a rather basic question about gate sets. So the notion of efficiency, does that depend on the gate set that you're using? Because say you had some gate set G, so in the discrete
Yeah.
case, say you had C naught, H, and T, and then you can approximate any unitary according to this gate set. But say you had some unitary U that is inefficient in this gate set G. Now, if I created another gate set G prime, which is like G union this unitary U, now all
Yeah.
of a sudden like unitary U is efficiently simulable in G prime. So does the notion of efficiency depend on the gate set, or is it kind of
No,
consistent for both discrete
no,
and like continuous?
yeah, it's a great question. It doesn't, and it's kind of fantastic. Like one of the contents of Solovay Kitaev theorem is really, you give me any universal gate set, so any set of gates such that when you combine the sequence, you get something that is dense in the space of unitary operators. And no matter the choice of universal gate set, the algorithm will still work the same and produce a short sequence of unitary gates. And in fact, this is what I've written here on the slide, and it's kind of this fundamental result that is somehow still part missing. I mean, we can discuss, but part missing in the CV case, which is that it ensures that the computational power that you get is independent of the choice of the universal gate set. In particular, there will be no cases where, let's say, you have a single qubit gate that I can super efficiently approximate with one gate set, but not another one. If the gate set has the power to approximate the unitary, if it's universal, then it can always do so efficiently. And this is nice because if I didn't have that, this would mean that I would need to make the difference maybe between, let's say, BQP when I'm using HC not T, BQP when I'm using H and Toffoli, BQP when I'm using match gate and swap, and so on. Like, you'd have to define one complexity class per choice of universal gate set. And I want to emphasize that this is how things are done in the CV case so far. So like the theory of the complexity theory for Bosonic system is sort of just starting. And so far, you have different complexity classes based on different, based on different gate sets. And and this is essentially, I mean, related to some of the open questions that are here.
Yeah, thank you.
Okay, so I'll ask one probably last question. You have another question? Okay, yeah.
In that Solovay theorem, you mentioned short sequence, right? Like, what do you mean by short there?
So let's say you want to achieve an overall precision. Let's say I'm comparing this guy on the top with the last one. So I'm trying to approximate my infinite dimensional unitary evolution by my sequence of the ones generated by polynomial Hamiltonians. So the quality of the approximation is measured by this thing, the energy constraint diamond norm. Okay, some norm, let's say, some operator norm. And you're going to quantify that quality with an approximation parameter. So this is this epsilon that you were seeing in the unitary truncation theorem. And by very short, we mean that in order to get to a precision epsilon in this norm, you will need order log or polylog, sorry, of 1 over epsilon gates. So yeah, essentially scaling with like log of 1 over epsilon. But I want to emphasize that I'm hiding something here, of course, because it's efficient in the precision, but it's not efficient in the dimension. So this is one of the open questions here. If you look at the Solovay, what we're using as a subroutine here is the Solovay-Kitaev theorem in finite dimensions for qubits. And for qubits, the complexity in the local dimension d of a qubit is actually terrible. I think it's exponential in that local dimension. And so this would imply that when we're using Solovay-Kitaev in CV here, we need to pay this price, like this exponential in d, and that d is going to be our effective dimension. So the thing that depends on the energy, and that effective dimension itself is like scaling potentially with epsilon and so on. So it's efficient in the sense, okay, in epsilon things are okay, but if you want to, if you want to do it in practice, even for gates that generates a small energy, this is not going to be very efficient. So to me, it's kind of a first step towards a full-fledged Solovay-Kitaev, which is why I left this open question here. But as far as precision goes, it's sufficient. Yeah.
So any more questions? Okay, I can finally ask my last question. Okay, so my question is actually very straightforward. So the question was, it has to do with the choice of bases. So I think in the beginning you said that you choose this number of particles basis or number of boson spaces, and then you put a cutoff by looking at the average number of particles, right? Is it can one choose? Like, does the entire thing depend on the choice of the number basis? Like, if you chose a different number basis and imposed the same constraint, would you end up with a different theory, or?
Yeah, that's a good question. So what I can say for sure is if you have a Hamiltonian that has a discrete spectrum, then you get the same theory, because there's this one result that we use, which is that, like, if you have energy constrained diamond norms, then when you are looking at the difference or the distance in this norm between two unitary channels, you can simplify it quite a lot. So you can remove you can show, and this is the same for the usual diamond norm for qubit channels. You can show that typically when you're thinking about distinguishing quantum channels, you allow yourself to use entanglement with another subsystem. But for unitary channels, you can show that this is not necessary. And so this simplifies a lot the proof, because now, this is the only thing that we need to bound, supremum of like just a trace distance bound on the subspace over pure states, like very simple. And this result being true, like in infinite dimension for energy constrained diamond norm. So this comes from that paper. And so from a follow-up of that paper, and I don't know how critical it is for the proof to hold, but it relies on the spectrum of the Hamiltonian being discrete. Yeah. So if you were, for instance, measuring the energy with, let's say, like actually your energy operator was position, then I wouldn't know. I think the fact that we're cutting off on a countable basis is kind of essential to the proof. Yeah.
So you're saying that if you cut off on the position in like continuous variable basis, then it's not clear what happens, because that also physically seems reasonable, right? Because you're saying that at most, I don't know, p square is bounded, right? Like the momentum is
absolutely No, it's just like, maybe mathematically you could make it work, but also like the truncation would not be a finite dimensional operator somehow, right? Because you could truncate the interval of position, and then I think these kind of arguments would still work, but it's not. Yeah, you're not reducing it to a finite dimensional object. So I think having
it's not
at least having part of the spectrum that is discrete, like you could have some hybrid Hamiltonian where like the spectrum is discrete and then it's continuous, but you cut off the continuous part. I think this would still be fine. But other than that, no, I think it's kind of critical to get something finite dimensional out of it. Yeah.
I see. So just to make sure that I'm following. So if you take any discrete basis and you cut it off, then you would essentially get the same theory of universality and so on. Am I getting it right? Or
I think so. I'd have I think that's right. One would have to kind of double check, because so N, the way we measure energy here, and Q and P, they are related in some way.
Right.
And so you might want to, let's say if you had a different Hamiltonian with discrete spectrum, you might want to extract out of this like the equivalent of Q and P for that Hamiltonian maybe. And then with respect to polynomials in those operators, everything would hold the same. But I can't remember right now if we're using the link between N and Q and P, but there is some structure here that's, I can't remember if it's instrumental to the proof or not, but I could check. Yeah, that's a good question.
But I think I was asking something else. So the set of physical operations
would it be the same, or would the set change? Because I think what you're saying is that if you use a different basis, then you can likely derive a theory of universality for those classes of operations that I'm calling physical.
Yes.
And but
Yes.
what
No,
I'm asking is the set of physical operations depending on the choice of discretization.
Yes, it is. Yeah, absolutely. So I can. Can I do this? Yeah. I think, for instance, if you're just cutting off in position, you could have states that. I think you could have states that have infinite energy that are only supported on a cutoff space in position, but crazily unbounded in momentum, in such a way that there would be finite energy from the point of view of position, but infinite energy from the point of view of number operator. So no. So I think.
I see. Okay. I'll bother you more later. Okay. I think we're past time, and I don't want to waste everyone else's time because I think I'm getting carried away.
No, but thanks a lot for the very interesting questions. Yeah.
No. Well, thank you so much. And yeah, let's thank the speaker again.
Thank you.
All right. I'll call you separately. Okay. I'm gonna hang up.
Sounds good.
Okay. Ciao.
Ciao. See you. Bye-bye.